interesting for us in the next meetings, start chatting about this, start talking, and discussions, new discussions. Next participant is Thomas Fabula from Köln, Germany.
Hello, Peter.
How are you?
Thank you. So, you can give me the screen, or should I?
Go ahead.
Can you see my screen?
Not yet.
Can you see my screen?
No, not yet.
No.
Bildschirm freigeben. Now?
Not yet.
Yes.
Yes.
Now.
Yes, yes, yes.
Okay. So thank you for inviting me, and we'll make the presentation models. Can you see it now?
Yes.
Yes.
Okay, I have to.
Just disappeared.
So now you can see it, yeah?
Here we go. Yes.
Yes, yes.
Starting in the, okay. So
PowerPoint presentation. Good.
you can see it, yeah? So thank you for the online conference today. And as you know, software is eating the world. I have adapted this to Forth Software is Eating the World. In fact, I started Forth in the 80s. As I mentioned before in talk with Peter, I studied physics in Bonn, starting in 1980. And as you know, Bonn was at that time the capital of Germany. And today the university is 200 years old. And at that time, in the 80s, 90s, Forth was very appealing to get into the physical world because of the measurements and for data acquisition systems. So we have a very good physical institute. Maybe you know Wolfgang Paul. When I left the institute or the university in 1887, he got 2 years later got the Nobel Prize for Physics, and he was awarded for some special spectroscopic things. I was also working on this, but in another group, and this was a very good motivation because our faculty of maths and natural sciences was really good. So this was a topic of my diploma thesis, and the task was to build up from scratch a real-time data acquisition system for high frequency and also for laser spectroscopy. And we use this for atomic spectroscopy in the Applied Physics Institute department. And we had a very old system. This was an old Z80, Zilog Z80 system. And before this, we also had a Digital Equipment Corporation. This was a PDP-8 system. So this was, let's say, an analog computer, not analog, but very discrete. Yeah. So it was from 1968, I think. So the thing was that I should build up a modern, at that time, PC, XT, extended technology, coupled with a slave computer. And this was a Europa card bus system. So this was modular. And we decided to take Forth because of the real-time capabilities. And we needed some acquisition rates in the upper kilohertz range. And the thing was that I built up the system, we programmed it, and also made some measurements. And this was to verify the functioning of the system. We took the hyperfine structure spectra of zirconium, and I wrote also some simulation programs, but this was on a high-level language with Turbo Pascal. So this is the experimental setup. What you can see here, it is for measurement of the hyperfine structure of, let's say, zirconium. We had an argon ion laser, dye laser, and we had a frequency control about this Z80 laser interface. And we had the hollow cathode tube here, where the gas was under test, and the whole data acquisition system was built by me, and it was the main topic to see this and to get a new experimental setup and new experimental possibilities. As you can see here, the system, I won't go to the PC because this is more than 30 years old, but at that time this was appealing. It was just the XT, and after this was the 80 advanced technology, and IBM was the de facto industrial standard. But we used the Z80 because this Zilog CPU was very robust. We had good software for this, and we had already from the electronic department a fourth kernel for this. So I used a fourth on the main computer, on this host computer on PC, but also used this fourth on the subsystem and implemented a FIFO, first in, first out parallel transfer possibility to steer the computer and the experiment, and to have an interface box where we had some different counters and some frequency, voltage to frequency converters and so on, and some I/O channels. So this was a very versatile interface box to several experiments. So here you can see it. We had some photon counters or some error signals, and we use this, I will go to this more in detail, to have a very cheap analog to digital converter. And we connected this to a market cavity who give us the frequencies of to compare it from our measurements. And we get this into our Z80 subcomputer to get it later into the main computer. So we get the main signals from the experiment through analog this setup. And the thing was that we had a TTL output. So we had a very easy way to have an analog to digital transformation by using this VFC62 chips. At that time, this was, I think, a very good idea. And we had to implement this, and it was very successful. Another thing you can see here, we had the fields, also the first in, first out measurement these devices connected to parallel ports of the PC. And this was a direct connection. So we could have a very high transfer here for data transmission. So during laser spectroscopy, we could focus on the real-time capabilities of the subsystem, because as you know, the PC has some lag. It is not real-time capable, because some of the interrupts are for the clock and also for the RAM refresh. So we couldn't use this. So we combined both worlds, because we had a lot of know-how in the 8-bit controllers on the one hand, and on the other side, we used, of course, in the 80s then the upcoming PC technology. What you can see here is a terminal program was implemented in LMI Force 83. This was, I think, version 3.1. Maybe Peter, you know it, or the other guys. And we had a host here, and this was running in an own mode, the slave system, and we could trigger it and had to steer it by this PC. What you see on the next slide is a memory map of the Z80 system. We had here the force kernel, then the measuring program itself, some data and comments. This was a data range, and we had some for the fourth buffer, and this was a normal setup of, I think, 64 kilobytes. Here you can see some timing diagrams where we were sweeping the laser frequency up, and we were counting here. And on the other side, we had some inputs from the experiment, but also from the calibrating gate, so we could see which are the signals and how to get this frequency, where are we in the frequency range, and to get the right information and to have a proper data set for later for the analysis. Here you see a hardware setup. This is the interface box. We had some cards. As I mentioned, this was a ECB, called in German Europa Card Bus. I don't know whether you know it, or at that time this was very well known. Here you see double Europa format. I think this is VME was, yeah, the name was VME. And we had some of the cards implemented in here. And we used also the same cards we had used before in experimental setup, but the new thing was that we used a real-time capable force subsystem and combine it with a PC, because before we had a CPM 2.2 or CPM 3.0 system, and this was of course not the fastest one, and we wanted to switch to the PC world. And as I mentioned, the PDP-8, it was only historic. So a good friend of mine, he finished his PhD, but after this, I think it got to the museum. So on the next slide, you can see the connection between the PC host and a Z80 slave, the master and slave. We had parallel FIFOs, and appealing feature was that we could scan. So scanning, analysis, and display of the measured spectrum was now possible in real time, and we could divide it. So make the scans and the data acquisition on the, as I mentioned, on the slave system. And we had the mass data transfer and later the analysis and things like this, simulation on the, comparing with simulations on the PC. So this was, I think, a very good new feature. And as you see here, Echtzeit means in German the real time. This is the real time capability. Everything else was post processing, not in real time. So here are some spectra of zirconium isotope shifts we measured, and this is what we had got with the system. This was a comparison to another measurement before, and to see where are the peaks and where to look for in the experiment. I wrote also a simulation program. This was at that time Turbo Pascal. It was fully implemented on a PC. It was fast enough, and you could play with these factors. I don't want to go into details, but to see, okay, what is bandwidth and where to see or where to look for the signals. And we switched between this simulation program and during measurement to see, here are some peaks and where to look for, and to have a good comparison. And I think this was also good to learn a lot of insights about hyperfine structure and things like atomic spectroscopy. So in the end, I want to conclude that this was, in the time 85 to 87, a PC-based data acquisition system was built up, and we used at that time the Z80 slave computer, and we could perform high-resolution laser polarization spectroscopy. And due to the utilization of a two-processor system, we think we had a very fast system response and could perform very fast measurements. And the real-time capabilities are within the slave computer, and the FIFO buffers were very responsible for this. And on the other side, we had standardized components, because at that time you could buy a lot of hardware, interfaces, and software for the PC. Of course, at that time it was very, it was not cheap, but the labor of students was cheap. So the professors used us to get this implemented, to implement. But I think for analyzing spectroscopy data, it was very good. And we had also the opportunity to add some commercial software packages later on, but this was not my job anymore, because we showed this was running, and it was enough to get the experiment running. So if you want to have some more information about this, we had made also a publication 88 in the Journal of Physics E. So it's about scientific instruments. There's also a link, I will send it to you. And this was the final remark, and I want to thank you, because I use this for to present also in a paper at the Deutsche Physikalische Gesellschaft. We had this at that time in Bonn, and after this I left the institute. I went to the south part of Germany, and I made some more applied physics, but in the field of micro-electromechanical systems. And this was the time where microsystems were born, let's say, we had good cooperation with Bosch, and we developed sensors. You use sensors like this every day in your smartphone, and I think this was a very good basis to understand these things. And from that on, I never used force, sorry, so this is some years old ago, some decades, but it was a very powerful tool, and I could cooperate with the electronic department and also with the old guys. And I think this was a good combination for force to have high level and a very machine so this means on a machine level, combine it and to have both advantages of both worlds. So this is it. Thank you. And yeah, if you have some questions, please feel free.
Wonderful, Thomas. Excellent.
Thank you. Thank you.
It's amazing. In your presentation, you spoke about, well, in the documentation, it said 4 millisecond acquisition time. That's very quick. Well done.
Mm-hmm.
I have a question, if allowed. How do you define real time?
Yeah, that's good question. Yeah.
Thomas, please stop screen sharing.
Okay.
I kind of wonder how much other researchers continue to use DOS because of its simplicity in research.
You mean DOS or what?
Yeah, DOS.
Mm-hmm.
Yeah, all DOS.
So MS-DOS, you mean, yes?
Yeah.
Yes, MS-DOS.
Yeah, the thing was, we had different institutes. Our institute was in the building of the mainframes. So we could use the mainframes for post-data analysis, but not for real-time or for experimental control. So real-time means what is sufficient for our experiments. So for our experiments, it was sufficient to have this resolution. Of course, if you look at the CERN, so high energy physics, they have another definition of real-time. But we decided to have this PC-based, or before this we had the CPM systems, and we were limited by the interrupts of the PC. So we use this two processor system. And other institute, they had some digital equipment cooperation measurements equipments, or even some extra equipment. So it was dependent of the institute who is running the experiment. But for our laser spectroscopy and atomic spectroscopy, this was sufficient and enough.
Thank you.
Okay.